understood yet. Okay, so what we can do? Here I propose a fairly basic, make a fairly basic proposal, try to understand the foundation of entanglement and the probability description of quantum mechanics. So what we can do? We need the requirement. So in the beginning, you should do not have any entanglement to study with. If you already beginning with the entanglement, nothing can discuss continually, right? So you do not have the entanglement beginning with. And also, no interaction involved for the entanglement production. And then third, there's no probability feature to begin with. So those are very strong requirements. And then, whether or not it is possible that by solve quantum evolution deterministically, okay, I emphasize that you need to solve the quantum evolution deterministically, whether or not we could show that at some kind of simple condition, the quantum evolution can precisely reproduce the classical dynamics. And at what kind of certain circumstance that entanglement emerges. So they contain two kinds of consequences at different conditions. So that's what I'm going to explore. Okay, so a realization of such proposals, the setup, we study with a couple of two photonic modes through the beam splitting. That's a very, very simple system. Probably the most simple system that in the quantum mechanics that can be easily implemented and realized in experiment. So the Hamiltonian of such a system is simply like in this way. This is the first mode, this is the second mode, and then can be exchanged the photons through the beam splitting. It's simple enough, right? So as everybody knows that such kind of Hamiltonian cannot generate entanglement itself. Then we study initial state. The state is a direct product, is a separate state, so that you don't have entanglement to beginning with. And also, those are the pure state. I will explain a little bit of detail. Those two are pure state. So now probability to state with. Okay, although everybody accepts the probability interpretations, but we try to not use such kind of interpretation to study with. So it's quite clear that satisfies the requirement we set up, right? Then we just simply solve the quantum evolution of such a system. You have the initial state, you have the Hamiltonian, you can solve it. That's a very simple problem. What we want to find is that at what condition the quantum dynamics will produce precisely the classical dynamics. Probably in all kinds of quantum systems, there are only one example that you can give such a realization. And then in other conditions, we find that entanglement will emerge. Okay, so now let's do. Okay, so this is the initial state. Actually, the alpha here, many people working on quantum optics is very clear. It is called a coherent state. What means a coherent state? It has a fixed shapes. And then the time evolution is just follow the classical trajectories of the harmonic oscillator all the time. If your initial state is a coherent state with a simple harmonic oscillator Hamiltonian, it will never go away of the classical trajectories. So that's the way no behaves. In fact, this was originally discovered by Schrödinger in 1926, just after he developed the quantum mechanical theory. And later on, this data was applied by Glauber to develop the quantum optics. So this is what it really looks. It's a wavepact, but it's oscillation in the harmonic potential if the system is go around. And then the second mode we set up in the coherent square state. So S equal to this gamma is real number plus time phase. So that's called the squeezing parameters. So squeezing parameters is different than the coherent state. it has a different shape in time evolutions, right? So everything is defined very clear. And if you don't know the detailed properties, you can go to the review article I wrote about more than 30 years ago, and about the new book which it published last year. Okay, so what is the solution we can have? This is a problem that every student who has taken the course of quantum mechanics can solve it, right? It's simple enough. It's easy enough to solve it. And then what you can get? Actually, you get two kinds of solution. For example, if you take the squeeze parameter equal to 0, you will find that the total state is keep in a separable state. There is no entanglement. If the squeeze parameter is not equal to 0, then eventually the state will become a non-separable state. Or in other words, it is the entanglement state, the entanglement emergence. But if we only solve such a kind of solution from Schrödinger equations or from Hessenberg equations, actually, you only can get such kind of conclusions, but you cannot see how the entanglement emerged. That's a key point. So everybody can solve the problem, but it's really hard to understand how entanglement emerges. So let's go some other ways. So we found that if you use Feynman's path integral in the coherent state representations, so you can precisely trace the motion of each mode. And then, in terms of the classical dynamics, path integral is the direct connection between quantum and classical dynamics. And then you will find that the real physical picture of entanglement emergence will appear. Very amazing. Okay, so let's see. So in order to give audience a simple picture, let's look at the simple system, how the coherent state will be the unique quantum state that gave you precisely the classical dynamics. So this is the quantum solution, right? You can do the simple calculation with the Schrödinger equation. The evolution solution will show you that it is still in the coherent state. And then this is coherent state changing in time with these factors. And this is the classical trajectories. So you can use the same way to solve it in path integral. And then the path integral in this kind of simple Hamiltonia is the path integral, all kind of paths. Suppose the path integral is defined as that all different kind of paths has a contribution to the quantum mechanics. But for this specific problem, only the stationary paths contributed. All other paths actually have no contributions. So you solve the stationary paths will give you the exact quantum mechanical solution. And meantime, you solve the problem in terms of classical mechanics. So the solution, as you see, that is already gives you the same, right? And then you take the amplitude, you can describe the wave vector, how it evolutioned in time. And the wave vector has equal quantum fluctuations in the position and the momentum. So the shape of the wave function never changed. That's why we can define the coherent state as a classical particle. Okay, now, this is a simple example. Now let's make the same calculation for the more complicated system. That's the system we're looking for. So because it's included two modes, two systems, and probably they are separated far ways. So we only need to stick on one mode, how it is changing in time. So we need to trace out another mode. Then use the path integral approach. The one mode, for example, mode 1, the density matrix is given by this evolution operator, right? It's clear. And then use the path integral. It is a little bit complicated, but the picture is still clear. So the evolution for the mode 1 is determined by the S1 is the action of the mode 1 plus a very complicated function f here. The f actually called the influence function that initially introduced by Feynman and Fanoz. Now in the literature, it's called the fine for non-influence functional. Okay, so those are the detailed derivations, and you need to just